Okay. So we are doing, now we have these functions within a context. So a lot of these are going to be, you're probably going to have these for your free responses on your test. So it's good to go over how you'll see accumulation functions. Okay. Okay. So for example, most of the time now, they're going to start by giving you a rate. And the reason why they start by giving you a rate is that now you can actually integrate it to get back to the original, and you can take the derivative. So they can test two things at once when you when they start by giving you a rate. So if this rate is in gallons per minute, if you integrate the rate, you end up with total amount of gallons from 0 to 5, right? Yes. Okay, so all we have to do is integrate this. Let's do u sub for it plus 1. du is just dt. Okay, so we don't really have to do much to integrate. We're just going to go from 1 to 6 this time. And then square root u, and then du. Okay, so it's easy integral. And then we integrate square root u, and we get 2/3 u to the 3/2 from 1 to 6. And then it's 2/3 times 6 to the 3/2 minus 2/3 times 1 to the 3/2, but that's just 2/3. Okay, and you get your answer, and it's about 9.131 gallons. Now, when you're in this class, you're going to round everything that you do in the calculator to 3 decimal places always. If you don't round to 3 decimal places, then I can't give you the answer for the point for this answer. So like always round to 3 decimals. Yeah.
If they did simplify that, it's the right answer.
Yeah, it's okay. Okay, got it? All right, this one, they're giving you a rate. The velocity is the rate, and that's in miles per hour. So if you integrate the miles per hour, then you end back at miles. So this would tell us how far or how much we traveled from 0 to 3 miles, or 0 to 3 hours. So if we integrate that, that would be 1/3 t cubed plus 3t squared plus 12t, and then we plug in 0 and 3, and we get 27 over 3 is 9 plus 27 plus 36, which is 72 miles. Okay? Got it? Easy? All right. Now, so then once we know these two concepts, we have fundamental theorem of calculus back up here, but rewritten. This is kind of like the thing where I told you to do fundamental theorem was like integral from a to b of f of x dx equals f of b minus f of a. And I said, if you don't know this, you can still use your calculator to integrate it, and then if you know one of these values, you can solve for the other one. That's essentially what we're doing here, is like you have an initial value plus, so this is your initial value that they give you, plus your total change from a to x. And if you have your initial value and then you add the total change from a to x, that'll tell you where you are at x. So this is an important formula for you to know. Okay. For example, if we were doing this problem again, this water tank problem, flip to the next page. If we're doing that problem again, and I said, oh, there's 120 gallons of water in the tank initially, then all you would have to do is to find how many gallons are in the tank at the end. You would do 120 plus your total change from 0 to 5 of root t plus 1, and you would get 129.131 gallons. So the difference between this one and the one we solved here is this tells us how many gallons were added in from 0 to 5. This one tells me how many total gallons are actually in the tank because I started out with 120 to begin with. Okay, so it's different. If I just ask you how many gallons are being pumped in, then I just want the integral. If I'm asking you how many gallons are in the tank, you add the initial 120. Okay. Same with the second example. If I said it's the car's 57 miles from its starting point, and then traveling after 3 hours, where is it? Then you would do 57 plus your total change from 0 to 3, and then you would get 57 plus 72, which is 129 miles. So this is your actual location, but the other one that we solved for was how much change we went from 0 to 3, how much we traveled from 0 to 3. But this is our actual location. Okay. Do you get the difference between those two concepts? All right. So that's one of the styles of free responses that you might see is water going in, water coming out, or a velocity or a rate, and then you need to find out where you are, how far you traveled. Another example that happens quite often is they actually give you an integrally defined function. So they say that this function is some sort of integral right here. Okay, so they'll give this to you a lot, and then they'll give you a graph of the f of t. So this is the graph of f right here. This is f. Okay, so that graph is f, and it's saying g of x is the integral of f of t. So let's find some of these values. If I plug in 0, what's the integral from 0 to 0? Still 0. If I plug in 1, what's the integral from 0 to 1? 2. If I plug in 2, what's the integral from 0 to 2? This is 3, so this will be 5. Okay, from 2 to 3 is 1, 2, right? So the integral from 0 to 3 would be 7 now, right? And then g of 6 would be integral from 0 to 6 would be, this is 2, and this is 1, 2, no, this is 2, and this is 1. We're back to 3, yep. And then 7 would be 2, right? Okay, cool. Now, this happens a lot too. It'll ask you on what intervals is g of x increasing. So if we look at this, where am I increasing on my original graph? From 0 to 3, right? I'm increasing from 0 to 3. I'm increasing from 0 to 3. And how do we know on this graph that I'm increasing? It is what? Positive, right? It's above the x-axis. So if it's above the x-axis, then I know that my g of x is increasing. Now how we write that, and this is, they'll give you a point for doing this, is that you'll want to write a connection between g and the graph that you have here. So g prime is what happens when I take the derivative of this integral.
It's just f.
Yeah, it's just f with x plugged in, right? and then times 1 minus f of 0 times 0, so that goes away. Okay, so if I want to know when it's increasing, I'm looking for when this is positive, right? So g prime is f of x is positive. Well, f of x is positive from 0 to 3. Everybody see that? Okay, cool. Now, where does g have a maximum value? How would you know that? Yeah, so it has a maximum value right here at 7, right? At 3, 7. So this is our max right here. But that's because the graph goes from increasing to decreasing right here. How do we know that on this graph it's positive to negative down here? Okay, so where does g have a maximum? G has a maximum when g prime of x or f of x. You always want to relate it to the function given to you, and you're given f of x. And then you would say goes from positive to negative, because the graph you see goes from positive to negative, and so that tells you that g has a maximum, because if g prime equals f of x goes from positive to negative, you know that your original is going from increasing to decreasing. So where does it have it? At x equals 3, and then max is 7. Okay. Now if we sketch a graph and I plot these points on this graph right here of g of x, here's another connection that you should make. So we're at 0, 0, 1, 2, 2, 5, 3, 7, 6, 3. I'm going to plot 5, 5 again. Yeah, thanks. And then 7 and 2. All right. And then how do you connect these? Well, you can see increasing to decreasing. It's very easy to see that. But now let's talk about concavity. When my first derivative has a slope of 0, then what kind of concavity do I have?
0.
0. So this right here is a straight line. So from 0 to 1, I have no concavity. It's a straight line. Okay, from 1 to 2, am I concave up, concave down? I am doing what on my first derivative? My first derivative is increasing, so my second derivative is positive, and my original is concave up, right? So now we're concave up a little bit. And then from 2 to 3, I am increasing or decreasing? Decreasing, so I should be concave down from 2 to 3. And then from 3 to 5, I am decreasing, so I'm still concave down. Concave down from 3 to 5. And then from 5 to 6,
0.
straight line, yep. And then 6 to 7, I am increasing, so concave up. So that's how you draw a pretty good graph of your original equation, Elsa.
In B or in C, since in B you said that like g prime of x equals f of x, do you have to say that again in C? Or is
You don't need to say it again. Once you've said it once, you don't need to say it again. Yeah. If you want to start all these problems right after you see g of x equals integral 0 to x of f of t dt by saying this is your first thing you say, then you can use it in all of the other problems. So you might as well just start with that, one of those statements connecting. Yeah, good question. Okay, So I want you to try example 4 and 5 and see if you can plot those given that integral, and see, and let's see if you can get to the same thing I'm at. Alright, so try 4 and 5. Do you guys have any questions on example 4, Gabe?
Yeah, how do you do this? Oh, he has this change to that.
6? Oh wait, what's 6?
I can do
Oh,
that.
this?
Cool. Yeah, you
It's just f of 10 minus f of 0. So f of 10 is 6, f of 0 is 0. So 10 is 6 minus 0 is 6. Okay, ready to let's do the next one together. So this one starts at 3 now, not at 0. So if I start at 3, what's my integral from 3 to 3? 0. Okay, I'm going to write it on this side so that I have extra space. Okay. If I know the integral from 0 to 3 is 4.5, then what's my integral from 3 to 0? Negative 4.5. Cool. All right. Then let's figure out let's do some easy ones. What's my area from 3 to 4? 1, 2, 3.5, right? What's my area from 3 to 6? 1, 2, 3. 3 to 6 is 6.5? 7, yeah, 7.5. Let's go 3 to 8 is 4.5, right? And then 3 to 10 is 1.5. Okay, so let's just plot a few. So here we are at 0, we're at negative 4.5. Then at 3, we're at 0. At 4, we're at 3.5. At 6, we're at 7.5. At 8, we're at 4.5. And at 10, we are at 1.5. Okay, what does this graph look like? What kind of translation? Yeah, it just looks like a vertical translation, right, of the same top graph? Right, just the only difference was where my 0 is. So for this one, when I start at 0, then my 0 is at 0, 0. But when I start at 3, then this whole graph moved down and 3 became where my 0 is. So x equals 3 is my 0 of the g. But it's the same exact graph, it's just shifted up or down. G of 0 is now negative 4.5. The domain is still 0 to 10 because I can still find area from 0 to 10. And then total change would be G of 10 minus G of 0. Sorry. And 1.5, thank you, minus negative 4.5 is still 6. So our total change is still 6. Our maximum is now 7.5. But it still happens at x equals 6, right? And what's my range? It's from negative 4.5 to 7.5. Okay, so not much has changed. It's just my starting value. I'm still increasing in the same areas. I still have my maximum at the same x value. I'm still decreasing in the same areas. Concavity stays the same. The only thing was it's a vertical transformation. So if we look at all graphs of this form, then these are just vertical shifts of each other. And what point will always lie on the graph given any family member? K comma 0. So every time if you go from K to K, you'll always get 0. So that's always going to be your 0 of your graph. Okay? This does the same thing. It says the same thing. So as K takes on different values, the functions f of t dt graph as vertical transformations of one another, each containing the particular point K comma 0. Even though the lower bound changed, is the derivative still the same? Yes. Okay, so it doesn't matter what that lower bound is, this derivative still stays the same. Okay? Cool. We're gonna, you can do this problem if you, no, let's just do the first part at least. So you're assuming f of -3 is -8, so it's giving you an initial condition, and it wants you to find f of 2. So knowing that I start here at -8, so this is at f of -3, my y value is -8. If I'm going from -3 and I want to find f of 2, what do I do to the -8? Yes, add the integral from -3 to 2, so we add 10 and 26. So we add 36, and we get 24. So f of 2 is 24. If I want to find f of 6, I start at -8. I add the 36, then I take away 8, and I add 14 to get all the way to 6, and I get 34. F of -5 means I go backwards, so what should I do to the -8? Add 18 or subtract 18? Which one? If I'm going from -8 at -3 to -5, yeah, we subtract 18. So we get -26. Yeah.
Isn't A 28 roughly?
Oh yeah, thanks. You're right. Okay. Got it? This one I'm going to save for you guys at the end. But let's talk about particle motion. Okay. So particle motion 2.0. I know.
No, unit 4.
Oh, unit 4, yeah.
Are we going to do two-dimensional motion?
Yep. This is one directional motion. We'll do 2. But not right now. Okay, position is still S of t. Okay. But if we're talking in terms of velocity now, you would want S of some k, right? Your position at k, your whatever's given to you, plus your integral from k to the number that you want of velocity. That's how you find position if you're given velocity and then one location. Okay? So, average velocity is S of B minus your position at A over B minus A. But written in integral form, you could actually do the integral from A to B of velocity. And that's the same thing. My B's really messed up. It's the same thing as this, right? Because if I integrate velocity, I'm going to get position, and then I plug in B minus plugging in A. So those two mean the same thing. But if you were in AB last year, you learned that these have two special names. What's this name? Everybody should know this one. Average rate of change, right? A-rock. And then this one is, no, you're just saying it. That's for mean value theorem. This one is average value. Do you guys remember from AB? Don't worry about it. We'll talk about these two names later. Just know that you can find average velocity either way. So if you have velocity and you need to find average velocity, you've got to integrate it and then divide it by B minus A. Instantaneous velocity is V of t or S prime of t, the derivative. Or, nope, that's it, just that.
Couldn't you express in terms of acceleration?
You could, but then you would need a one initial velocity
Okay.
plus, you know, the interval. Yeah, so I didn't want to do that because you're never really going to see that. Speed is absolute value of velocity. Still, don't forget speeding up. What's speeding up?
When the acceleration and velocity go in the same direction.
Okay, velocity and acceleration, same direction. This is velocity and acceleration, opposite direction, right? Okay, don't forget those two things. Acceleration is the second derivative of position or the first derivative of velocity still. No problems there. Displacement is the, what is displacement? S of B minus S of A only. So that's displacement, your position at B minus your position at A. If you're given velocity, it's the integral from A to B of velocity. Okay. So, when you integrate velocity, that equals this anyway, so that's displacement. And then distance, what you want to do is you gotta, like, if I had, for example here, if I have any negative area, for distance, you add that in. So what you want to do for distance is you want to integrate the absolute value of velocity from A to B. So you want to make all of your graph positive before you integrate it. It doesn't make sense to do the absolute value outside of the integral, because if you do, all you're doing is finding displacement and then making it positive. That doesn't do anything. So distance, make sure your absolute values go inside here. Okay, let's do one last example and then we are done for today. So we've got this particle. Oh, so this is the third type of free response that you might see. So one was the accumulation. The second one is this integrally defined function. And then the third type is a particle motion. I'm basically telling you the three types of free responses you're probably going to get on the test. But you'll get 2 out of the 3. So if you prepare for those 3 types, then you should be good on those free responses. Okay, So we got a particle, and we have an initial position of s of 0 equals -3. I want the displacement from 1 to 7. Do I care about my initial position if I'm doing displacement? No. We have no care about where we started. We just need to know how far we traveled from 1 to 7. So integral 1 to 7 of negative t squared plus 7t minus 10 dt. Okay. And we'll get, negative t cubed over 3, just negative t cubed over 3 is not in the exponent, guys. Plus 7t squared over 2 minus 10t from 1 to 7. And then, I have it already for you. That answer, if you plug in 7 and 1, you get -6. Okay, cool. I'm not going to make you do that. That would be a lot. Okay, total distance traveled is different. You got to go integral 1 to 7 of absolute value of velocity, negative t squared plus 7t minus 10 dt. Okay. Now, if you have a calculator, it's super easy. You just type this in, and then you're done. Oh, I don't have a calculator. Can you do? Okay, so if you have a calculator, it's not hard. It's just math 9, 1, 7, and then to get absolute value, math over to number. The first one is absolute value. Negative x squared plus 7x minus 10 dx. Okay. And your answer is 15. Okay, so this equals 15. But what if you didn't have a calculator? What would you have to do? Yeah, so if you didn't have your calculator, what you would need to do is you would need to find when this changes direction. So you have to take that, the velocity, v of t, which is negative t squared plus 7t minus 10, and set it equal to 0. Let's pull out a negative. Oh. Did I do that right? Yeah. And then we get t minus 5, t minus 2, right? Okay. We do a number line at 2 and 5. And then you can test values, but I know that it's a negative quadratic, and negative quadratics go negative, positive, negative. Easy. Okay, cool. So, I mean, if you looked at it here, like negative x squared plus 7x minus 10, if you look at it on your calculator, it goes negative, positive, negative at 2 and 5. And if you do absolute value of that, it takes the whole graph and it makes everything positive. So it flips all of the negative parts up. And so when you find area from 1 to 7, you can also find area on your calculator too. If you go second calc number 7, and then you go from 1 to 7, it'll shade all of it for you. It finds that area. It's 15. But let's say you don't have your calculator and you've got to do it by hand. This is what we're doing here visually. we would have to go, well, the integral from 2 to 5 is fine. But the integral from 1 to 7 and from 1 to 2 and 5 to 7 are negative, so we need to make them positive. So there's 3 ways you can make that positive. The first way is all you have to do is put a negative outside and go 1 to 2 of v of t, and then add it to the positive part. So that's one way of making it, this negative part, positive. Another way of making it positive is doing, just add it, but then flip it and go 7 to 5 of v of t dt. That makes it positive as well. And then a third way of making it positive is you could go integral from 5 to 7 of v of t dt, but then just put absolute values around it at the very end. But you don't really see this very often. You either see it with the minus or with the flip of the bounds. Anyway, so you would have to do this and plug in 2 and 1, and then plug in 5 and 2, and then plug in 5 and 7 and subtract them, and it's a lot of work. But whatever, you can do it. It still equals 15. Probably on a standards quiz, I'm just going to make you set up the split, but I'm not going to actually have you evaluate the split. Okay? All right, and then the last problem, what is the position of the particle at 4 seconds? This is the one where we actually care about our initial position. So what we want to do is we want to go -3 plus the integral from, my position at 4 equals -3 plus the integral from 0 to 4 of v of t dt. And then you can just use your calculator to get it, and -8 1/3 meters is the answer to that question. Okay, do you understand the difference between the 3 things? So that is particle motion, part 2. All right. We're done for today. Do you guys have any questions on anything?